Writing balanced net equations for acid-base reactions is usually easier than for redox reactions. As long as we start with the primary acidic species and primary basic species, the products are simply the conjugates of the reactants. So in writing balanced equations, we need one acid and one base, since one reactant will donate a proton and the other will accept a proton. If we're given two reactants, it's important to determine which reactant will be the acid and which will be the base. Usually that's straightforward, but remember that some materials are amphiprotic, so they can act as either an acid or a base. We can use the acid-base chart to help us out with this. Once you know which is which, then you can identify the hydrogen that transfers. We need to be sure to use the primary acidic and basic species. Finally, we can write the formulas of the products, as they are the conjugates of the reactants. Again, the acid-base chart can help out if we need it. And since these are net equations, no spectator ions are included. Let's try some examples. First, write a balanced net equation for the reaction between HF and NaCN. Since HF has a hydrogen and NaCN does not, we should easily see that HF will be the acid. Just to confirm our suspicion, let's consult the acid-base chart. By the way, we will need to consult the acid-base chart to determine if a reaction is extensive, which we'll do in the next video. But we also need to know if either the acid or base is strong, because we need to know the primary species. We find HF in the section of the chart that has weak acids. So we know the primary acidic species is aqueous HF. The other reactant is sodium cyanide. Notice there are no sodium ions appearing in any entry on the table. That is because the sodium ion is a spectator ion in Bronsted acid-base reactions. It doesn't have a hydrogen, so it can't be an acid, and being positive, it won't bind to an H+. We find cyanide in the base column in the section for weak bases, so the primary basic species is aqueous cyanide. On the reactant side of the balanced equation, we have HF and cyanide, both aqueous. Since there is only one hydrogen, it is easy to identify the H that transfers. So the products of the reaction must be fluoride ion and HCN, both aqueous. Our next example asks us to write a net equation for the reaction between sodium hydrogen sulfite and phosphoric acid. Sodium is a spectator ion, so we look for HSO3 1- and phosphoric acid on the acid-base chart. We might expect HSO3 1- to be amphiprotic since it has a hydrogen at the beginning of the formula, but also has a negative charge. In fact, we can find it as an acid and as a base. So which way will it go? It depends on the other reactant. Phosphoric acid acts as an acid and as an acid only, so by default HSO3 1- will be the base. Since phosphoric acid is a weak acid, the primary acidic species is H3PO4. The primary basic species is the hydrogen sulfite ion. The reactants in the balanced equation are HSO3 1- and phosphoric acid. The hydrogen that transfers is one of the H's on phosphoric acid. So the products are H2SO3 and H2PO4 1-. All species are aqueous. Notice how the products are conjugates of the reactants. Our final example is the reaction between perchloric acid and KHS. KHS is another amphiprotic material. We should be able to identify this as an ionic compound, where the potassium ion will be a spectator in the same way as sodium has been in our previous examples. HS 1- has a hydrogen, so it is a Bronsted acid, but also has a negative charge, so it can be a Bronsted base. Consulting the acid-base chart, we can find HS 1- on both the acid side and the base side. What it does will depend on the other reactant. We find perchloric acid way up at the top of the chart on the acid side, so HS1- must act as a base in this reaction. In assigning the primary species, we need to be careful, since perchloric acid is a strong acid. That means that the primary acidic species in this case is the hydronium ion, H3O1+. The primary basic species is HS1-. The reactants in the balanced equation are the primary species, hydronium and HS1-. The hydrogen that transfers is one of the H's on hydronium, since that is the acid. So the products will be water and H2S. Notice here that the reactants are aqueous, as is H2S. However, water is a liquid, so we need to be careful with our bookkeeping.